Ma'am, enable the screen sharing, ma'am. Hello, ma'am. Hello, ma'am.
Yes, sir. Yes, sir. I did it, sir.
Yeah. Sorry, students. I was thinking the class was tomorrow, so it was a delay. Sorry for a few minutes. All right. Hello, everybody. Good evening.
Good evening, sir.
Good evening, sir.
Good evening.
Good evening, sir.
Yeah, good evening. Yeah. So we'll continue. Today it will be theory, a lot of theory. 3 derivations we'll have to do. That for the 12th standard. So you need to learn those 3 derivations. We will learn those derivations. Before that, we will learn other concepts from the yesterday's class. We'll continue. Closed packing arrangement we learned. Now, continuation of that is interstitial sites in closed packing. What do you mean by interstitial sites? Now, if I have a sodium chloride crystal, sodium ion is positive, chloride ion is negative. Likewise, if sodium ion positive, chloride ion is negative. Likewise, we have a layer, 2 different layers, assume, like this. If any particle from its original lattice position occupies the space between the 2 layers, then those sites are called as interstitial sites. What do you mean by interstitial sites? Particles from its original lattice points, if it occupies into the space between the layers, they are called as interstitial sites. Even in closed packing of the spheres, there is left some empty space between the spheres. These empty space in the crystal lattice is called a site, or it's called as a void, or it's called as a hole. These voids are of following types. I told you what is interstitial sites. The space between the two layers is called as what? Interstitial sites. Now, this empty space in the crystal lattice is called as sites, or it is called as voids, or it is called as holes. Voids are of following types. The first one will be called as trigonal void. What do you mean by trigonal void? The site is formed when three spheres lie at the vertices of an equilateral triangle. Size of trigonal site is given by the following equation. Now, what is this trigonal void? Triangular void. Now, we have three spheres here. Now, each sphere, there is a nucleus here at the center. So this nucleus at the center, if we join, you can see you get an equilateral triangle. Equilateral triangle. So the space here, the site is formed when three spheres lie at vertices of the equilateral triangle. Size of the triangular site is given by the following relation. See, this space, this empty space is called as what? The void, trigonal void. So trigonal void is formed when three spheres are in contact with each other in the form of an equilateral triangle, and the space at the center will be called as what? The trigonal void. And the size of the trigonal site is given by the following relation. This is called as R. R is equal to 0.155 capital R. What is the small r? The small r is called as radius of the spherical trigonal void. The radius of the spherical trigonal void. We will learn about this relation in detail in a topic called as radius ratio. We will learn it today. What is radius ratio? What about this? What is the small r, capital R? All that we will learn. Now, you should remember what is trigonal void. A space between, now if I have three spheres like this, if I represent three spheres like this sphere, this empty space, this void is called as trigonal void. Did you understand this?
Yes, sir.
Now, tetragonal void. What is this tetragonal void? A tetragonal void is developed when triangular voids made by three spheres in one layer touching each other, having contact with one sphere either in the upper or in the lower layer. It's a clear explanation. It clearly says this is a trigonal void. If there is one more particle placed like this above or below, you have now four spheres are in contact. Can you visualize what I'm telling?
Yes, sir.
Yes. Now, when four spheres are there, there will be a void in between. That void is called as tetrahedral void. So tetrahedral void is made when four spheres are in contact with each other. Three will be at the bottom and one will be above, or the above one particle can below the three particles. So that will be called as a tetragonal void. The relationship is R by R is equal to 0.225, or it is called as radius ratio, or it can be written also R is equal to 0.225 capital R. So this relationship we will learn, I told you, in the following sessions. Now, where R is the radius of the tetrahedral void of an atom and capital R is the radius of the sphere. So R is the radius of the tetrahedral void. What do you mean by tetrahedral void? Here they clearly explain. Now, there will be a space here. You imagine you are keeping three tennis balls here like this, tennis balls here like this, and one above. When you keep one above, the fourth tennis ball you're keeping above. So what happened? There will be a space here. In that space, the radius is represented as small r. And the radius of this ball itself, the tennis ball or something, or the sphere itself, that radius is given by capital R. Do you understood the difference between the small r and capital R now?
Yes, sir.
Yes. You have to visualize and understand this. Now, octahedral void. What is this octahedral void? This type of void is surrounded by six closely packed spheres. That is, it is formed by six spheres. You can see the bottom layer is shaded in a gray shade, and the above layer is in the broken lines. You can see three. Totally, there are six spheres. The space between these six spheres, we have octahedral. When we have six spheres, it forms octahedral structure. So the space in this is called as octahedral void. The radius of that space is represented by small letter r, and radius of each sphere is represented by capital R. So therefore, the relation is r by r is equal to 0.141 r. We can write this as small letter r is equal to 0.414 capital R. This relationship you should know. This is called as octahedral void. Now coming to cubic void. What is this cubic void? Cubic void is formed between eight closely packed spheres, which occupy all the 8 corners. So if you understand that in the room where you are sitting, you have 8 corners. If there is nothing in the room, then the space present in the room will be called as what? The cubic void. It will be called as cubic void. 8 corners, 8 particles, and the space, complete space, will be called as cubic void. And the relation is r by r is equal to 0.732, or we can write this as small letter r is equal to 0.732 capital R. This is the relation. Now, the decreasing order of the size of various voids, decreasing order. Cubic void is spacious. You can see it's spacious, bigger compared to octahedral. Next, it's tetrahedral and trigonal. This you should remember for your competitive exams. Okay, the spacing of the voids. Cubic void is largest. Next comes octahedral. Next is tetrahedral, and trigonal will be the. Yes. Yes. Anybody? Any doubts? Any clarification? Anybody asking me anything? Hello, are you there in the class? Respond to me. Can you hear me?
Yes,
Students,
sir.
can you hear me? Madam, can you hear me? Hello? Hello?
You are audible, sir.
I'm audible. No, people have to respond, man. All right. Okay. Anyways, now we will try to understand one term. What is that we are trying to understand? That is called as coordination number. Coordination number. Now, what is this coordination number? Now, I will take an example of a cube. I'm trying to draw here. I don't know, the space will be okay. No, I will draw it here at the bottom. The space is more here, I believe. Yes, I will draw here. What is this coordination number? This is a cube I'm drawing. And cube has 8 corners. And in the corners, we have particles. I'm representing a particle like this. In a different color, I'm representing. And one more particle I'm representing at the center of the cube. I'm representing at the center of the cube. Like this, I'm representing at the center of the cube. We'll give different color possibly, otherwise we'll see different color I'm giving here. Center of the cube. Now this is the red color. This is a different color. Now this particle which is at the center will be associated with this. This is associated with all the other 8 particles. I'm drawing a bond in a broken line. Yes or no? Yes?
Yes, sir.
This red is cesium. Red is cesium. This orange color, or this color, this is chlorine. Now tell me, is cesium bonded to 8 chlorine atoms? Yes or no?
Yes, sir.
Yes. Now what is this
Yes, sir.
coordination number? In case of solids, coordination number is number of particles associated with a particle which is under reference is called as coordination number. What is that? Number of particles associated with the particle of reference is called as coordination number. It's represented by Cn letter. Now, cesium is associated with how many chloride ions here? 8 chloride ions. Therefore,
8.
the coordination number of cesium will be 8. Coordination number of cesium will be 8. You understood what is coordination number. Now, I'm telling you, for sodium chloride. For sodium chloride, coordination number of sodium ion is 6 and coordination number of chloride ion is also 6. What you understand by this term? What do you understand by this? Can I say each sodium ion is surrounded by 6 chloride ions?
Yes.
Yes, sir.
And can I say each chloride ion is surrounded by 6 sodium ions?
Yes, sir.
Now you have understood the concept of coordination number in detail. This is the definition of coordination number in case of the chapter solids. There is one more chapter called as coordination compounds. There you have coordination number. That's a different definition. That's a different concept. Here, in terms of solids, coordination number is defined as number of particles associated with a particle which is under reference. Number of particles linked with the particle which is under reference is called as coordination number. Now you have to learn this. This is important. This is a regular question, as well as they can ask you on any competitive exams. Example for NEET also they can ask you. Effect of temperature and pressure on coordination number. See, the first is pressure. The next is the temperature concept. Now you see, when on applying pressure, sodium chloride structure having 6:6 coordination number. What do you mean by 6:6 coordination number? Coordination number of sodium is 6, as well as the coordination number of chloride ion is also 6. That is why we have written it as 6:6. Coordination changes to cesium chloride structure having 8:8 coordination number. That means when pressure is applied on a crystal, the coordination number of the crystal increases. Coordination number of crystal changes and it goes to a higher value. Actually, the coordination number of sodium chloride at normal condition is what? 6:6. That means each sodium ion is surrounded by 6 chloride ion and each chloride ion is surrounded by 6 sodium ion. But when you apply pressure, when you increase pressure, what happens? The structure itself changes. From sodium chloride structure, it changes to cesium chloride. Like this, it becomes. So it becomes now what happens? Here it will be sodium, and here all it will be what? Chloride. Each sodium will be surrounded by 6 chloride ions, and each chloride ion will be surrounded by 8 sodium ions. Therefore, on applying pressure, what happens? The coordination number increases. Followed? Followed?
Yes, sir.
Yes. Now, similarly, when you take cesium chloride structure, on heating cesium chloride at 760 Kelvin, very high pressure, high temperature, 760 Kelvin, what happens? The sodium chloride structure, cesium chloride changes to sodium chloride structure. That means what happens on increasing the temperature, the coordination number decreases. Increasing pressure, coordination number increases. Increasing temperature, coordination number decreases. Cesium chloride has coordination number what? 8:8. When you increase the temperature to 760, on heating it to 760 Kelvin, what happens? It gets converted to what state? Sodium chloride state. Sodium chloride will have what coordination number? 6:6. Did you follow this? This is important. You should know. Students, did you follow?
Yes, sir.
Yes, sir.
Yes. Yes. What happened? Now, this is important. Actually, in your 12th standard, this topic is removed. They are not talking about the radius ratio, but it is important for your competitive exams. What is this radius ratio? It is very simple. Radius ratio is defined as the ratio of radius of cation to radius of anion. What is cation? What is cation? Positive ion is cation. And what is anion? Negative ion is anion. The ratio of positive ion to negative ion is called as radius ratio. Why we have to study radius ratio? I'm telling you in 2 minutes. Now, always remember, anion will be having greater size compared to cation. Anion will be larger than what? Cation. So when anion is larger than cation, radius ratio will be less than or equal to 1. It cannot be more than 1 because the denominator is what? Having a larger value. Anion is what? Larger in size. Since anion is larger in size, radius ratio should be less than 1, or maximum it can be what? Equal to 1. Now, what is the purpose of learning radius ratio? The purpose of learning radius ratio is, in modern days, we have something called as spectroscopic techniques. Spectroscopic techniques to find the structure of the molecule, to find the structure of the molecule. So in modern days, there is an instrument, many instrumentation techniques like UV spectroscopy, you have infrared spectroscopy, you have microwave spectroscopy. We have, you know what is infrared rays, what is microwave rays. You would have heard of microwave rays, you would have heard of UV rays. Based on all those radiations, techniques are developed. Those are called as spectroscopic techniques. Those spectroscopic techniques can be used to find the structure. But in earlier days, when spectroscopic techniques were not known, they used the concept of radius ratio to find the structure of the molecule, to find the geometry of the molecule, or to find the shape of the molecule. Now, see this. If the radius ratio is what? Radius of cation to radius of anion. If radius ratio is less than 0.155, then the coordination number is 2. You know what is coordination number? Coordination number is 2. A particle associated with 2 other particles. Therefore, the coordination number of this is 2. Correct what I'm telling? I've just wrote the letter N, okay, randomly. Don't think it has any atom or element. Okay, if a particle is associated with only 2 other particles, then we say the coordination number to be 2. When the coordination number is 2, then the structure of the molecule or the shape of the molecule, they've written as a type of the void here, it will be linear. The molecule will be linear. When I say molecule will be linear, now for an example, beryllium, not beryllium, we can take an example for any crystal. What crystal we can take? Beryllium fluoride. Beryllium fluoride, if you can have like this. Beryllium fluoride. This is a linear because beryllium is in contact with only 2 fluorine atoms. It's a linear molecule. Now, if the radius ratio is between the range 0.155 to 0.225, then the coordination number is 3. That means each particle will be associated with 3 other particles. Then the structure will be called as triangular planar. Triangular planar, boron trioxide. This is called as boron trioxide. The structure will be what? The triangular planar. You should know this tabular column. You should know this chart. If the radius ratio is between 0.225 to 0.414, coordination number is 4, then the geometry will be tetrahedral. Example, it is zinc sulfide, cuprous chloride. Likewise, if the radius ratio is between 0.414 and 0.732, coordination number is 6. When coordination number is 6, the geometry will be what? Octahedral. The structure will be octahedral. Sodium chloride, magnesium oxide are few examples for the crystal with octahedral geometry. And if the radius ratio is between 0.732 and 1, then the coordination number is 8. Coordination number 8, when we say it has a cubic structure, cesium chloride, ammonium bromide is the example for coordination number with 8, and the structure is cubic. If the radius ratio is exactly 1, then the coordination number is 12. Closed packing, whether it's cubic closed packing or hexagonal closed packing, most of the metals will have hexagonal closed packing, and the coordination number of pure metals will be what? 12. Example for copper, zinc, etc. Any other metal, gold, silver, all metal, pure metals, they will have coordination number 12. See, once you know the radius ratio, you can find the coordination number. Once you know the coordination number, you can find the geometry. That is the relationship between radius ratio and coordination number. Is there any question? This chart you should remember. You should remember this chart. Any clarification with the students so far?
No, sir.
Anybody else? Any clarification you can ask? This is a lot of theory. Today it's a lot of theory. We are not working numericals. Once we learn the theory part, then we can go for the numericals. Now, it's time for you to be more concentrating, because we are going to learn 3 derivations which are there for your classes. One of the derivation will be there in your 12th exam. So you should be in a position to concentrate more. Now, what is this packing efficiency? The percentage of total space filled by the particles is called as packing efficiency, or it is also called as packing fraction. Now, for an example, I have a box. If I fill this box with 50% with this water, maybe I'm filling it with water. Now, exactly, and if I measure how much of water I've filled, maybe if this, assume that this container, volume of this container is 1 liter. Volume of this container is 1 liter. I take 500 ml water bottle and pour this. Here, 500 ml water bottle, I buy one and I pour into it. So now tell me, how much is packed here? This is 1 liter capacity and I poured 500 ml of water. So what will be the packing efficiency? How much I have packed? How much has been filled?
Sir, the half, sir. 50.
Half. It's half means it is what? 50%, right?
Yes, sir.
50%. So 50% we have filled and 50% is empty. So the percentage of total space filled by the particles is called as packing efficiency, or it is called as packing fraction. It's called as packing fraction. So we'll have to learn the packing efficiency or the packing fraction. Now, in order to find the packing fraction, the formula what you will be remembering is this. Packing efficiency or packing fraction is given by the formula volume of the sphere by volume of the unit cell. Volume of the unit cell. Now tell me, what is the volume of the sphere? You're all learning mathematics. What is the volume of the sphere?
4 by 3 pi r cube.
4 by 3 pi r cube. Pi, you know, it's a constant value, and r is the radius. You know this. Correct. But do you know the volume of the unit cell? You
8
don't
by
know the volume of the unit cell. You should find out the volume of the unit cell. So this is the final equation I gave you, because we are going to learn the packing efficiency of simple cube, body-centered cube, as well as face-centered cube. In order to find the volume of all the 3, the final equation what we will be using is this. Packing efficiency will be equal to volume of the sphere by total volume of, by volume of the unit cell. Now, in case of simple cube, now I will draw a cube like this. Simple cube I will draw. I will draw a simple cube like this. All right. I have drawn a simple cube. Maybe the diagrams may not be very clear, but you have to manage with what I'm trying to explain. Now, I draw a particle at this corner like this. And there is another particle here. It's an ionic compound. There is an ionic bond. So this is at this corner, I'm drawing one. And at this corner, I'm drawing one. This corner. So totally 4 particles. This is the center of the nucleus. These are the center of the nucleus. Can you visualize what I've done?
Yes, sir.
Yes. Now, when I say you have visualized what I've done, now this distance is called as edge length. This distance is called as what? Edge length, and represented by letter A. And this distance is called as radius, represented by R. Do you understand? So this length completely, this adjacent atoms are there, no? That length, this length, complete length is called as what? Edge length. Edge length we represented by letter A. Edge length is represented by letter A, and the radius is represented by small letter R. Is it clear? So far, is it clear?
Yes, sir.
You understand what is edge length and what is the radius? Now, the assumption is let the edge length of the unit cell, let the edge length of the unit cell be a letter A, small letter A. And the radius of the sphere be small letter r. So this is what we have learned. The edge length is what? A, and the radius of a sphere is small letter r. The spheres are touching each other in closed packing arrangement. See, in closed packing arrangement, the spheres are touching each other. 4 spheres are touching each other. Yes or no? Yes, maybe if I write only this, I will represent it like this for our understanding. I will represent this for our understanding. Only this face I'm taking, the upper face, and I'm writing here. So this is the nucleus, this is the nucleus, this is the nucleus, this is the nucleus. So if I join, I get a square like this. And this length is called as what? Edge length A. And this distance is called as what? Radius. Same thing I've drawn here. This 4 spheres, I've represented it like this. Is it clear? Can you visualize, students?
Yes.
Yes. If that's the case, can I say, thus, edge length A is equal to twice R? Yes or no? See, if this distance is edge length, and this is the radius, and this is also the radius, no? So A is equal to how many R now? How many R?
2R.
2R. Or we can write R is equal to A by 2. Radius is equal to A by 2. Same thing, right? Yes or no?
Yes, sir.
Participate in the class, please respond. This is complex, no doubt about it. Now tell me, number of particles in unit cell of SC, simple cubic lattice. How many particles are there in simple cubic lattice?
8.
Oi, how many particles are there? One.
One.
Yesterday we did how many? 1. Correct. 1. And body center it is 2, and in face center it is 4. We calculated the problems yesterday. Okay. Remember, revise. So what is the volume of sphere? Volume of the sphere is 4 by 3.
4 by 3
Pi
pi r cube.
This you know very well. Now you tell me, what is the volume of the cube? Volume of the cube.
R cube.
Volume of the cube.
8R cube.
8R cube. Volume of the cube.
A cube.
Volume of the cube is length into breadth into height, no? Length into breadth into height. So here the edge length in this case, it is what? A. So this edge length will be what? A here. Can you see this edge length is A? So therefore, what will be the volume of the cube now? Volume of the cube will be A cube. Or this will be what now? 2R cube. Oh, this is what you told, 8R cube. Correct. This is 8R cube. This is what you told. Someone told me 8R cube. I was confused. This is what you told? Hello? Okay, anyways, the volume of the cube is what now? 8R cube. Once you know the volume of the cube and also volume of the sphere, now tell me, what is the percentage packing efficiency? Packing efficiency is what? I told you the formula, no? What is that formula? Volume of the sphere divided by volume of what? The unit cell. Volume of the unit cell. This is the formula, right?
Yes, sir.
Yes. But you should remember, in order to calculate the packing efficiency, what is the contribution of the unit cell? So what's the number of particles in the unit cell? So in the simple cubic lattice, how many particles we have? 1.
1.
If I'm working on body-centered cubic lattice, 2 particles will be 2. So I have to multiply this by 2. If I'm talking with respect to face-centered cubic lattice, I have to multiply it by 4, because face center has 4 particles in a unit cell. So that will be equal to 1 into 4 by 3 pi r cube divided by, what's the volume of the unit cell? Volume of the unit cell is 8R cube, sorry, 8R cube. 8R cube. On simplifying this, you will get pi by 6, that is equal to 0.524 That's equal to 52.4%. So when I say it is 52.4% is the packing efficiency in case of what? The simple cubic lattice. What is the empty space? Empty space will be how much? Empty space will be 100 minus 52.4. So it will be 47.6%. The empty space will be 47.6%. Mathematics might be wrong, you check. Did you understand this derivation? Did you understand this derivation?
Yes, sir.
Now what I want you to do is, I want you to take a minute or so and recollect what you learned. This is simple. The next complex. So I want you to go through this in 2 minutes time. I'm revising. I think the font will look small because I want the whole derivation to appear on this page. Let the edge length of the unit cell be small letter a and the radius of the sphere be what? Small letter r. Then a length is twice the radius. Our radius is what? A by 2. So number of particles in unit cell of simple cube is 1. So volume of the sphere is 4 by 3 pi r cube. And what is the volume of the cube? Here, in case of simple, it is a cube or 2r cube. Therefore, it's 8r cube. So on substituting that, you will get packing efficiency of the simple cubic lattice to be 52.4%. This you have to work. This you have to practice and be thorough. Next, we'll go for face-centered cubic lattice. The next what we have is face-centered cubic lattice. Now, this is a little complex. I want you people to pay attention. I want you to pay attention, right? At least this will finish for today, and body-centered cubic lattice will continue possibly in the next class. Let's see. Now, face-centered cubic structure. In this structure, on each face, the face-centered atom is touching the other two. I explain the other two spheres at the corners. Face diagonal, we will represent it as AC, and we will mark it as 4R. What is this 4R? You have to understand now. This 4R is important. Now, I will draw a cube. I will draw a cube like this. This looks complex. Pay attention. I will draw a cube like this. All right. 1 minute. I'll draw a cube like this. Now, at the corners, you have particles. At the corners, you have particles. This is face-centered cubic lattice. And I am showing only one particle at the center of the face here. I'm showing only one particle at the center of the face here. For our understanding, I'm showing only one. Now, this distance is marked as AC. This distance is marked as AC. And as usual, the edge length is A. Edge length is A. And we'll mark this as D. We'll mark this as D for our understanding. Now, what was understanding? AC is equal to 4R. What does this AC is equal to 4R means? AC is equal to 4R means what? Now, this is the particle, blue, which is at the corner, which we have marked as C. And this is another particle, which I'm drawing it in blue, which is marked as A. This is C and this is A. And this is the particle which is at the center. This is the particle which is at the center. Now, this is the center of the nucleus. This is the center of the nucleus, and this is the center of the nucleus. Now, if I join this, this is the radius of this sphere, This is the radius, this is the radius, and this is also the radius of the sphere. So what is this distance now? AC. AC is equal to 4r. Did you understand? Did you understand this? You followed or not?
Yes, sir. Yes,
Yes,
sir.
sir.
Now, as per the observation here, see, these particles are not touching each other. It is not so. They are in touching with each other. That's what it says. The face-centered atom is touching the other two spheres at the corner. This is what this face-centered atom is touching A and C. Therefore, AC is marked as what? 4r. AC is marked as what? 4r. Clear? Now, from the right angle triangle, from the right angled triangle, ABC. Not A, yeah, ABC. This is B, no? This is, I didn't mark this. ABC, if I mark right angle triangle, this is A, B, and C. This is a right angle triangle. Now, what will be AC? Tell me. AC square will be equal to what? AC square will be equal to what? AB square plus BC square. Yes or no? What is that theorem called as?
So
Pythagoras theorem. Yes. AC square will be equal to AB square plus BC square. What will be AC? AC will be square root of AB square plus BC square. Yes or no?
Yes, sir.
Yes.
Yes.
What is AB? AB is
A
given by
square
what?
plus A square.
Very good. Square root of A square plus A square. That will be equal to what?
2A cube.
2
A
two-
cube. A cube.
2A cube baruta. See, 2A cube.
Yes, sir.
It will be root 2A.
Root 2A.
It will be root 2A. It will be root 2A. You can write it as square root of 2A square. So it will be what now? Root 2 and square root. For A square, if you write, it will be half, no? So this will cancel. So it will be what? Root 2A. Correct, na? Yes or no?
Yes, sir.
Yes. Now, can I say 4R is equal to root 2A? 4R, because AC is what? AC is 4R.
The AC is 4 hours. So yes.
4R. So we can write 4R is equal to root 2A. Or what will be A? A will be equal to 4 by root 2R. 4 by root 2R. I'm just taking this denominator. That's all. Root 2, I'm taking it to the left side in the denominator. So I write A is equal to 4 by 2 root 2. 4 by root 2R. Or we can write R is equal to A by 2 root 2. R is equal to A by 2 root 2. This relation, this three relationship you should know, because they can ask you problems based on these three relations. Okay, so these three relationship between the radius and the edge length of the simple cubic lattice. 4R is equal to square root of A, or A is equal to 4 by root 2R, or we can write R is equal to A by 2 root 2. Students, is it clear?
Yes, sir.
Others?
Yes, sir.
Yes. If that is the case, tell me what will be the volume of unit cell? Volume of unit cell will be what? Volume of unit cell will be is equal to what? A cube. When I say it will be equal to A cube, edge length, no? So it will
4R
be 4
divided
by
by 2 root 2.
root 2R the whole cube. 4 by root 2R the whole cube. On simplification, 4 cube is 32. 32, and it will be what? Root 2R cube. R cube. This is the answer. On simplification, you get 32 by root 2 into
64.
R. Yeah, 64, and this will be 2, no?
Sir,
2
yes,
root.
sir.
64
2.
divided by 2 root 2.
Yeah, okay. 64 divided by 2 root 2 is what? 32 by root 2, no? These two will get cancelled 32 times. Yes or no?
Yes, sir.
So finally, the answer is what? You're right. 64 by 2 root 2. That is nothing but 32 by root 2 R cube. This is the volume of the unit cell. Now tell me number of spheres in FCC, number of particles in FCC. What are the number of particles in FCC? Number of particles in FCC is how much? 4. Now tell me what will be the packing efficiency? Packing efficiency. packing efficiency will be equal to 4 into 4 by 3 pi r cube. Because what is the volume of the sphere? Volume of the sphere is what? 4 by 3 pi r cube. Divided by, what's the volume of the sphere now? We found the volume of the sphere to be 32 by root 2 r cube. On simplifying this, you simplify mathematics, I'm not that confident of. You simplify this. On simplifying, you'll get 0.74. Since they're talking about percentage, multiply by 100, it's 74%. 74%. Any clarification here? Any clarification here? Please participate. There are 10 students in the class. You
No,
should
sir.
tell me. You should tell me. Just check and tell me. Go through once. You should know that what is this 4R? Why you have taken AC? What is this 4R? If you understand that, then the things becomes easy. So in face-centered cube, okay, center of the face, there will be a particle. Center of the face, there will be a particle. This particle, which is at the center, will be in contact with these two. That is what we have written. A and C, this is the particle at the center of the face. So this A and C distance, this edge length, this distance is what? 4R. AC is 4R. So based on that, AC square will be equal to AB square by into plus what? BC square, all that. And we found out A is equal to 4 by root 2 R, or R is equal to A by 2 root 2. So A is called as edge length. This relationship you should know. What has been put in box, you should know this relationship to work out problems in your competitive exam. This derivation will be for your regular POC class. This derivation will be for your regular POC class. All right. Yeah.
Yes, sir.
Yes. Now, one more derivation, if I go, it will take time. Body-centered cubic lattice. Shall we do it in the next class and then continue with problems in the next class? Yes?
Yes, sir.
Yes, sir.
Madam, can I?
Sir?
Man?
Yes, sir. Yes, sir.
It will take time. Okay, bye.
No problem, sir. You can continue in next class, sir.
Okay, ma'am. Okay, ma'am. Okay.
Okay, sir. Thank you, sir.